Okay, the next thing we're going to talk about is mobility. Now, we've already gotten a taste for how to create kinematic diagrams using kind of this simplified standard process or standard symbols using a couple of these examples. But now what we want to do is we want to make sure that how we have things labeled lines up with how this is going to function. And this is what we call mobility. So mobility is how many degrees of freedom are needed to operate this mechanism. And so a degree of freedom is the number of independent inputs that are required to precisely position all the links of the mechanism with respect to the frame or the ground, okay? So we want to make sure that when we calculate our degrees of freedom, that it comes out to what we're expecting to happen. So for instance, if we have 1 degree of freedom, that means I only have to do one thing in order to make this mechanism go, okay? And ideally, that's where we want to be, okay? But if there's more, that's okay. It's just that it's not going to be as easy to operate, okay? So as we look here, we can calculate the degrees of freedom using what we call Grubler's equation, okay? Grubler's equation. So Grubler's equation is going to be equal to F, degrees of freedom, is going to be equal to 3 times n minus 1 minus 2jp minus jh. So n in this case, lowercase n in our equation, is the number of links, the total number of links. So the total number of links, we look at our kinematic diagram. So we're going to create a kinematic diagram first. We're going to put all of our links in place. And we're going to put in here how many links we identified, okay? So the number we've been using lately is 4, right? Number 1 for the frame, 2, 3, 4, or however many there would be. There can be more than 4, but the last 2 diagrams that we did, both of them were 4. So our n would be our total number of links. And this is going to be the number with the circle around it on our diagram, okay? What was the highest number? And then you're going to notice that we have minus 2 times jp. This is the total number of primary joints. So J is a joint, P is for primary, okay? Primary joint is either going to be a sliding joint or a pin joint, one of those two, okay? So those are going to be our A, B's, C's, and D's, and E's and F's, or whatever the letters are. We're going to count up how many letters there were. And then minus higher order joints, okay? Higher order joints are going to be cams, gears, chains, and we're not going to be looking at those until later in our studies of basic mechanisms. So this last part we can just truncate. So if we just stop this at 3n times n minus 1 minus 2jp, you can be done because we're not going to have any cams, gears, or chain drives, okay? So the JH would just go to 0. Now, the numbers that we have here, whatever number we end up with is how many degrees of freedom. So again, it's the number of things I have to do to get this mechanism to function, okay? So number 1 is ideal. That means I only have to do one thing in order for this item to do what it's supposed to do. So earlier, when we had that toggle clamp, what the operation is basically I'm going to move that clamp, just that clamp handle, or I'm sorry, just the handle, and it's going to clamp in the front and it's going to do what it's going to do. So I only have to do one thing. So when I calculate the degrees of freedom for that mechanism, I should come out to 1, okay? For the vice grips that we just looked at, okay, if I look here, I hold this frame as it's stationary, I only have to do one thing. I only have to move my handle. That's one thing, 1 degree of freedom in order for that front to actuate and open and close, right? Okay. Now, if I had to do 2 things, I would have 2 degrees of freedom. If I would have to do 3 things, I would have 3 degrees of freedom and so on, okay? Ideally, when we're designing, 1 is our best number. It's what we call user-friendly, okay? But we also, you're going to notice that they say we call that constrained, okay? Now, if you end up with a 0, that means it's locked. That means that that's a frame. It's real. There's no degrees of freedom. So that means it's just a supporting type of a member. Okay. Now, if you end up with a negative value or 0 for any of the things we're looking at that we know are moving, then you probably either are missing a joint or a link call out. Okay. And so you just have to kind of find where that is, or you might have too many for some reason. Okay. And you want to look at that. Unconstrained is when we have something greater than one. So if we think about, for instance, I've never driven one myself, but a crane. You have multiple like levers that you have to actuate in order for things to happen the way it's supposed to happen. Not as easy to operate than one thing, when you just do one item. So again, it's not that you can't, or it's not a good idea, or it's a bad design if it's unconstrained. Sometimes you just can't get around it, but it's not going to be as easy to operate. Okay. Another one that you're going to come upon that's going to be greater than one, and I'll show you this already because this is going to be one of the assignments that you do for me. You're going to draw a kinematic diagram. You're going to be calculating this mobility, and that is going to be one of these playground scoopers. If you've ever done that, whether it's as a kid or you revisit it as an adult, it's not as easy to do as you would think because there's two levers that you have to actually actuate in order to get that to scoop and move and pull the way that you want it to. And so that's kind of like maybe a real life application that you might be able to relate to or you've done before, where it takes you a couple times kind of trying things out before you really get to be able to maneuver things. And it doesn't take might take a couple of scoops and then you got it and then you move on. But it's not as easy as if it was just one lever and then you move along. Okay. So, so just keep that in mind. As a designer, you want to always make things as easy as possible, and calculating these degrees of freedom will give you an insight of, number one, do I have everything labeled appropriately to how I anticipate or know it's supposed to function? But then also, if I've got multiple degrees of freedom, how does that affect, operating what I have here? So what we're going to do is we are going to go through the process of drawing a kinematic diagram. We're going to do it in CAD this time. And then we're also going to calculate the degrees of freedom using Grubler's equation, and then also kind of verifying the items that we're looking at. So the first example that we're going to do both of these on is going to be example 1.3. So example 1.3 is going to be found on page 9 in our book. Okay. And you're going to notice that it's going to be one of these toggle clamps. This is a different variation on the toggle clamp that we looked at earlier, but it operates very similarly, where we're going to actuate our handle, which is connected to the frame member here, so that the front side, the clamping portion, can go up and down, if you would, or clamp or not clamp. And then we're going to calculate those degrees of freedom to confirm that we are a degree of freedom of 1, and that it's considered what we would call a constrained mechanism. Okay. So to do that, let's go underneath our book, and you're going to notice at the top of page 9 here is the illustration for the toggle clamp. Okay. Now, what I want you to do is let's take a minute or two to just sketch out what we believe this mechanism would look like in kinematic diagram form. Now, if you look down below, they do have it done for you. I encourage you to not peek and just see how you do. Okay. So I'm going to, on the side, draw it, sketch it, if you would. And then what we're going to do is we're going to go over to AutoCAD and just kind of go through that process again of using our start file and getting it into the form that we would be handing it in for our practice problems. We will not be handing in the sketch for this practice problem, just the AutoCAD diagram, just so you know. Okay. But I think a sketch is in good order just to make sure we understand, how to identify everything. Now also add your link labels and your joint labels, as well as any special interest points that you feel should be there. Actually, it says in the problem here, it says in the problem, using the clamping jaw and the handle as points of interest. So you want to label each one of those. Okay. How did you guys do as far as the sketch? Okay. All right. So if you looked at yours, or if you look down below, you will notice that theirs looks like this. Okay. Which very reasonable. Mine is a little different. Okay. And mine is a little different in a couple ways. Number one, my labels aren't exactly how they did theirs. And that, remember, that's okay. The only one that has to be the same is going to be the frame. Okay. But then after that, the other ones can be relatively arbitrary. But what I did to mine is the front part here where the clamping area was. As a designer, this is the freedom that I have. It doesn't always have to be a triangle. You're going to notice the book does that a lot. But to me, there are two parts of that front clamping area that are important to me. Number one, down here where it's going to clamp, right? But then also, how far is this going to swing in and out? Okay. So I actually kind of added Z, if you would. I did an X, Y, and a Z so that I had a little bit more thickness here to represent more of the extents of that front part. Now, is that right or wrong? That's a designer's call. Okay. So if you did it the way the book did and just focused on that front part and just kind of kept it as a thinner triangle, totally fine. Good representation. But if you were like, how would I do that? I kind of am interested in that. You can change the shape. It doesn't always have to be triangles. Does that make sense? You can make more of a polygon. Now, notice that I did not draw what that adjusting screw would be or any of the elements there, really. All I did was kind of just draw a generic polygon of what the extents might be so that I could give a better representation of the space that it would take up. Okay. So now all I'm going to do is we're going to open up our start file. We're going to rename it example 1.1 or 1.3. And now we're going to draw the kinematic diagram in AutoCAD. Okay. So I'm going to switch over to AutoCAD and I am going to do an open. I'm going to navigate to my kinematic start file that I just created. Okay. And I'm going to rename it right away. So I'm going to do a file save as, and this is going to be example 1_3_ probably 2 or something. Okay, so just example 1.3 some way, somehow. And then I am going to now use these elements to create the diagram that we just sketched. So I'm going to move my frame over. So I always start with my frame. Let's see. Now I'm going to copy, turn off my ortho. I'm going to copy this one to be just a little bit higher. Seemed like it was. And now I am going to draw center. I think this went up and to the left a little bit. Oh, I didn't put it on the right layer. So I'm just going to reselect that and I'm going to put it on the object line layer, switch to my object line layer. And then I'm going to draw my handle endpoint here. I'm going to add my points afterwards. And then I'm going to draw to here-ish, down to here-ish, into the center here, and to the endpoint. There we go. And then I'm going to, now I don't require a slider for this one, so I can get rid of my slider right away. There we go. And then I'm going to copy my pin joint from its center to the endpoints where they need to go, which I think is just those two. Yeah, okay. Okay. Once these are in place, now I can get my labels and put them where they need to go. So I'm going to copy again. Number one, you can put it by either one of the frames because there's two connections to the frame, but only label one. Okay. And then I'm going to, let's see. I'm going to move my number two to here. I'm going to move number three here, and then move number four, just put it in the middle there. And then I'm going to move each one of my letters. So I've got letter A. It actually goes pretty quick. So once you know, and I suggest sketching out each one even before you go to CAD. That way you can kind of verify it's what you want it to be. And then the CAD part just goes super duper quick. And then I'm just gonna copy this. I'm just going to copy one of my joint labels. So copy, grab B here. I'm going to put it on the endpoint of my handle, endpoint and endpoint of my clamping area. And then I'm just going to double click and I'm going to call that X. Okay. X. Left click out. There we go. And then double click here. Y. And I do have that third one. Let's see. Special interest points are never going to be the beginning of the alphabet. They're going to be the end of the alphabet. That kind of differentiates them from joints. Okay. And then the joints are going to be the beginning of the alphabet. So I will do a quick save. And there is my example 1-3. Okay, so now we have our diagram done. But the second part of this problem is adding and doing the mobility equation. Okay, now as we look at this operation, the way that this operates is we just have the handle to move and it's going to clamp what it needs to. So we're expecting the degrees of freedom to be 1 when we do that Grubler's equation. Okay, so underneath the camera here, using, underneath the diagram that I created. Now, when we hand in, you only need to hand in the AutoCAD version. Okay, you don't have to hand in the sketch that you made. If you do, I'm not going to make you make that. But since I have the sketch here, right underneath, I'm going to do Grubler's equation. So Grubler's equation is F is equal to 3 times n minus 1 minus 2 times JP, okay? That's the equation in variable form. You always need to write the equation in variable form before you put any numbers in place, okay? If you had me for statics or strength of materials, I don't think anybody did. I don't think anybody did. Steve, you did. You had me for statics. You had me for statics. I'm a big write out the equation in variable form first. So that's what this is. You have to do this and then put your numbers in and then put the final answer. I don't want the final answer. I don't want you to say F is equal to 1. No. I want you to write this equation out. So write out the equation in variable form. Then we're going to put our numbers in place. So now remember, 3 is a variable or a constant, if you would. Now our variable is n. This is the number of links, okay? The number of links. You don't have to put that on there, but that's what n is. N is the number of links. Links are going to be what we identified as the number with the circle around it. So when we look here, we've got 1, 2, 3, 4 links, okay? So this is going to be 4 minus 1 inside the parentheses, okay? If you don't have 1 through 4 up here and you write 4, that's not right, okay? That's why we do the labeling first, because this kind of verifies what we believe is true. And then you're going to say minus 2 times the primary joints. This is how many letters you have. So I've got A, B, C, and D. That's 4 letters. 2 times 4, okay? X, Y, and Z are special interest points. They are not part of this equation, okay? Only links and joints. So only my numbers with the circles and my letters. That's it. And then when I do this math, this is going to be 3 times 3, right? So that's going to be 9 minus 8. F is going to be equal to 1. And you're going to put a box around your final answer. F is equal to 1. So the degrees of freedom is 1, which is what I'm expecting, right? I move the handle. That's all I need to do to make this clamp. That's one thing that I need to do. So this is considered a constrained, which is good. Degree of freedom of 1. Okay. Now, you need to add this to our example. Okay. Now, whether that is taking a picture of your manual calculation or adding it to the actual CAD file. So you could do a copy. Once you have your example here, you could write out, right? You have to write it in variable form first. F is equal to 3 times n minus 1 minus 2 times JP. Then you can put your numbers in and so on. Okay, so I'll let you play around with that. I don't want to take time to do that right now. Okay, but then you would put your numbers in and it could be part of your screenshot all in one. So you would have, for instance, the example, the diagram, as well as the mobility equation here with the final answer. So a couple more rows here. All right. You could take a screenshot and then you would add that. So I'll do my screenshot here. Here's my screenshot. And now I'm going to go back over to my Word document and I'm going to say, all right, Control V, here is my document or my screenshot for the last one. In this case, it would be including, so if I zoom in here a little bit, it would be including the work for the mobility equation. You have to add that full thing. Does that make sense to everybody? Now, if you didn't add it as part of the CAD file, that's okay. You could do F is equal to 3 times n minus 1 minus 2 JP, and then put your numbers in here. F is equal to 3 times 3 minus 1 minus 2 times 4, right? And then you would say F is equal to 1. You could do it that way as well, all right? Either way, so whether you include it up here or if you put it as part of your document when you're handing in, I'm totally okay with that. But I want to see both the diagram with all the labels as well as the mobility equation for example 1.3. Yes.
Even on AutoCAD, do you still want that answer boxed?
Oh yeah. The question that Steve had is if we do it on AutoCAD or really here, do you need the answer boxed? No, I guess it would be here. That's just another, it's really just showing me the work. So it's okay as long as you have F is equal to 1. Okay, at the bottom, that would be great. Kind of like we'd have here, duplicating this in one of the two places. Yeah, you wouldn't have to have the box. If you do it by hand and you take a picture, if you would, of this, then I just have to know that this is for example 1.3 and that this is the work for that. Does that make sense? Okay. So if you wanted to do all the mobility equations on one piece of paper and then just label each one for me, that's fine. Okay. So, but it has to be neat and I have to be able to follow it. So I guess you have 3 options here. Most students will do the AutoCAD version and put it all in the AutoCAD, one screenshot, and then put it over on the document. But you've got 2 other options, however you feel is best for you. Okay. So that's example 1.3. Any questions on that? So that's another one of the practice problems that we have, right? All right. Let's go back to our PowerPoint and see where we are at. Oh, example 1.4. Almost done. This is our last example that we're going to be doing. So example 1.4, you are going to find on page 10 in our book. Okay. And that is right here, example 1.4. Here we're going to do an AutoCAD diagram and again, a mobility equation. Now this is for a can crusher, okay? So the mechanism that we see here is you'll notice that there's a handle out front. It's connected to what would be the frame, which is this part right here. And then you're going to notice that there is the can crusher portion, which is on the top here, which is going to go vertically up and down, okay, to crush the can then, which would be in place at the bottom here. So what we want to do is we want to first draw the kinematic diagram, okay? And it says using the end of the handle as a point of interest. So out here is the only place that we would have a point of interest. And then it also wants us to compute the degrees of freedom, okay? So go ahead using this illustration. Now, you would only be looking at it from the side. They're kind of giving you a 3D view here, but you would look at it just going from the side. There's only going to be, this is going to be the handle, the connector, the slider, but don't show the other parts on the other side. It's a mirror image, if you would. So you're just going to look at it from one side. If you want to peek down further to see what they came up with as a kinematic diagram, go ahead. But I encourage you to try to do it yourself, or at least give it an attempt to start. Now we're sketching right now. You won't be handing in the sketch. It's not required to hand in this sketch. You will be handing in the CAD for this, okay? So we're just really kind of doing this as an exercise so that once you go over to CAD, I think it just goes faster once you have the sketch kind of figured out. So if you've, got your sketch and you kind of compared it down to the bottom, you'll notice that it's something like what we see here. Okay. So kind of going back and forth to kind of show you how they came up with this. First of all, the portion, this block that moves up and down, this is going to be that slider. It's going to be, if you would, constrained to be in a vertical direction. So that is the slider that is in this orientation. Notice that the frame portion that it is constrained to identifies the direction of the motion, which is going to be vertical, okay, in this case. All right. Then you're going to notice that if we look at the handle itself, the handle connects to what would be the frame, which is kind of this L configuration. Okay. Now, this is a straight handle. So you might be like, well, why don't you just draw that as a straight line? It wouldn't be wrong to do it, but if we only do it as a straight line, and I'm going to show you down here, okay? If I show it just as a straight line, okay? So this would be A, and this would be B. Do you see how this could look like two parts as opposed to one continuous part? By adding kind of that triangle for thickness, this shows that this is one continuous part as opposed to two separate parts. Does that make sense to everybody? That's the difference. That's why in this case, yes, it is a straight member, but you don't get that. It's not as easy to see. So for clarity, even if it's not as thick as I showed, if you just kind of show it nice and thin, just a little bit of thickness so you can see that, okay, that's a continuous part as opposed to two separate parts. Okay, so that would be the only thing that would separate that. But other than that, are there any questions on the numbering and the lettering? I started with the frame here. You could start the frame there. It doesn't really matter which one. There are, if you would, two connections to the frame, but you want to label one of them. Don't forget that by the slider, between the slider and the frame, there is a sliding joint. Okay, so that's where my joint D is. That's a slider joint or a sliding joint. All the other ones are pin joints. Okay.
You got the access, the input, and
Yep.
And then output would be like crushing rock.
Right. So you're like, do you need a point of interest there? For the problem, they said, draw the kinematic diagram using the end of the handle as a point of interest. That's the only one that they were interested in. Now, you as a designer, if you want to know, for instance, something that a kinematic diagram would go to would be like, well, how far is this going to move as I actuate this? That would be a module 2 problem, which we're going to be looking at. I don't know if we look at this example again, but that would be like, okay, let's now put that through its motions and find out what is the highest point and what is the lowest point, making sure I can fit a can in there or different size cans, and then how far would they actually crush down? So that's a little further. Right now, we're just representing in where it's at right here, frozen in time. What does that kinematic diagram look like? But you're correct. That's going to be a very practical answer that you would want. Okay. All right. So sketched wise here, any other questions? So don't forget D when you've got sliders. If you do, you're going to like do your mobility equation, be like, I'm not getting one. I'm getting something else, or I'm getting a negative value. That's not right. If you get a negative value, that isn't right for mobility calculation. Okay. So usually if it's a slider, you might have forgotten your D. Okay. So now let's translate this into an AutoCAD drawing, because that's what you're going to have to do. So I am going to open my kinematic start file. Okay. Open. And I am simply going to kind of move these items around. Move this over and down about here. Now for this one, I'm going to move my slider. This has to be in a vertical direction. So I have to rotate this 90 degrees in order for it to be vertical. I can't leave this as a horizontal. So I'm going to use the rotate command in the modify section. I'm going to select my slider endpoint, and then my base point is just going to be wherever. But notice that we need to identify the rotation angle. If you remember, a positive rotation is counterclockwise. So I would be rotating this counterclockwise. So I want this to be 90 degrees positive, okay? And then it's going to be vertical. All right, so that's going to be my, and I'm kind of looking at relationship wise. I think I'm going to move this down and over a little bit, okay? And then now I'm going to put in my elements. Yeah. Well, I can look at that separately, but when you want to rotate it, so you want to actually rotate it 90 degrees. Rotation is right here. Does that make sense?
Oh, I got it.
You got it? Okay, yeah. So then I'm going to add my lines for each one of my links. I'm going to go to the center here. And this one goes, I don't know, right about there-ish. And then I'm going to do another line, center here. Actually, I'm going to just draw a straight line. And center. And I'm going to go nearest. There-ish. And then I can add my pin. From the center to the endpoint. Then I need to add that little bit of thickness. So there. And then add my labels. Oops, I should rename this before I accidentally save it as the kinematic start. So this is going to be not the kinematic start. This is going to be sample 1_4. Save. And then I'm going to move my labels so that they are where they're supposed to be. And once you have that done, we need to do our mobility equation. So if you want to go ahead, if you're ahead of me, go ahead and get started on that. And we'll do it together in just a bit when I get mine in place. So your final diagram should look something like this. Oops, my D went away. I think I moved instead of copied it for my example. So I'll just copy my C here. And then switch that to D. There we go. So any questions on this diagram? Okay. So if we have the diagram done, then the last part of this is to do our mobility equation with Grubler's equation. So what I'm going to do is I am going to go underneath my camera and I'm going to add that mobility equation on here. Now, like I said, you can add it as part of the CAD diagram. You can add it as part of your Word document, or you can, take a picture of the hand calculation. So this is going to be example 1.4. Grubler's equation is F is equal to 3 times N minus 1 minus 2 JP. You could put minus JH, but remember those higher order joints are going to be 0 anyway. And this is going to be 3 times. Now our N, if we go back to our illustration, or I have it right up here, you're going to notice that's the number of links. So I have 1, 2, 3, 4 links. So that's going to be 4 minus 1 in parentheses minus 2 times the primary joints. That's going to be my A, B, C, and my D, which is 4. So that's going to be times 4. So this is going to be 9 minus 8. So my F is going to be equal to 1. Okay. And again, you can put this as part of the CAD file. You can put it as part of your document, or you can handwrite each one, letting me know which example is the calculation, and take a picture of all of your calculations. So now, if I go back to my AutoCAD here, I am simply going to do my screen snip of this, and I'm going to add this to my Word document. Okay. So now I'm going to go Control V. And again, however you want to add the mobility equation, whether it's part of the CAD, if you want to add it down here or add it as the hand calculations, it's totally fine as long as you have it here. Now, this would be the last of the examples that we have assigned for our practice problems, okay? So what I'm going to do is let's go back to our PowerPoint presentation and kind of finish up what's here, because we've kind of gone through the demonstration items that mimic the homework that you're going to do. So if I go down here, you're going to notice that the next section that we're going to go to is going to be the 4-bar mechanism. Now, I've kind of referenced this as we've gone through in class here, but many of the mechanisms that we're going to be looking at, almost, I'm going to say 95% of them are going to be 4-bar mechanisms, because these are the most popular that are out in industry that are going to represent mechanisms you're going to encounter. So a 4-bar mechanism is always going to have number 1 as the frame, as we know. Then our first link is going to be what we call our input. It's going to be where we impart motion for that mechanism to function. So we call that an input link. Many times that is going around in a circle or pivoting about a center. So a lot of times we call that the crank, okay? And then you're going to notice that connected to the crank is going to be the coupler or the connecting rod, which is then going to connect to an output link. So taking the frame and adding these 3 moving links, that is a total of 4 links in our mechanism. So that's called a 4-bar mechanism, all right? Now, there are a couple different types of 4-bar mechanisms, the most popular being the crank rocker, the double crank, and the double rocker. And those we can find on page, hold on, I don't have the page called out here. On page 20 in our book, okay? So the 3 most popular are going to be the double crank, the crank rocker, and the double rocker. These other 2 aren't as popular, but they're there too. So all that means is it's comparing the input to the output. So when we say double crank, that just means that both the input and the output are going in a full circle, okay, in their operation, all right? The next one here, the crank rocker, that just means that our output is going on a full crank. I'm sorry, our input is going around a full circle, a crank, okay? And the output is oscillating or rocking back and forth, okay? And then the third one is the double rocker. That means that our input is only rocking, it's not going in a full circle, and our output is also rocking, not going in a full circle. So this is going to be like the toggle clamps that we looked at. The handle was just going a portion, it wasn't going in a full circle, and then the clamp portion was also just oscillating or just rocking back and forth, not going in a full circle. Okay, and then the 4th type of mechanism is going to be, I'm going to go ahead here, the slider crank mechanism, okay? The slider crank mechanism is going to be like our can crusher that we just looked at, where we have the input either going around in a circle or oscillating, and then the output is going to be a linear motion, whether it's vertical or horizontal. So that can crusher, the that blade, that cutter blade that we looked at earlier. This is also another cutting mechanism. And then another typical one is going to be a piston in a cylinder bore, would be a very similar, it would be a crank slider as well, okay? Now, as we look at our last slide here, this talks about the techniques of mechanism analysis. So when we look at representing from here on out, you're not going to have to do sketches for me unless it's for your purposes to kind of organize your thoughts. But what you're going to be handing in for me is always going to be the CAD diagrams. So in CAD, the things that we demonstrated today that you need to know is, number one, you need to know how to draw a line, right? You might need to know how to draw a little bit of circles, put notes down. And then we're going to find later on when we start looking at moving these mechanisms around, you're going to be measuring displacement. So putting some dimensions in order or in place to be able to kind of analyze what's going on with that mechanism. And that brings us to the end of our PowerPoint presentation here. So as we look back at the practice problems. So today's lecture, we got through all of the elements that you can hand in for your practice problems. So if I go to Mod1 practice problems, ooh, there is one, and I'm going to take it off. I'm going to take it off because I think we did enough today. The last one we are not going to do. We're going to skip over 1.9. We did sketch only for 1.1. You just save this so that you guys can see it. Okay. Sketch only for 1.1. The AutoCAD diagram only for 1.2. This is the vice grips, okay? And then AutoCAD and mobility equation for 1.3. That was the second toggle clamp that we looked at. And then the AutoCAD diagram and mobility for 1.4, which was the can crusher that we just looked at. Now, once you have all of those in place, so it's 4 problems, sketch, and then 3 AutoCADs, then what you're going to do at the bottom of the Word document that you have all your diagrams in, you're going to answer these 3 questions. You're going to tell me what are 2 things that you learned in Module 1 here? What are 2 things that you still feel like you need some practice on? And what do you feel the main objective of this module was? Okay, that's it. And then once you have those answered, and it's all set, then you can hand in to the practice problems here. Now, a couple of items here. It says, use a scale and a straight edge for the kinematic diagrams. If you hand sketch that first one, I'm okay with that as long as it's reasonably straight lines. Does that make sense? Okay. Make sure that you show all your work like we talked about with those Grubler's equations, and then take a pic and upload the practice problem so that you can either convert it to a PDF or just save that Word document, and you can upload that Word document directly to it, and I can see it as well. If you have any questions about formatting, just let me know. But basically how we did it in class here is exactly how I want you to hand it in for the practice problem. So at this time, are there any questions? Okay. So by following along, you should have all the practice problems done. Now, as we look at the assignment, if I go back to Module 1 and we look at the assignment number 1, you can get started on assignment number 1. The next time we're together, which is Friday, it's going to be a work time, okay? And I will be available virtually, as we know, to go over any questions that you have. Now, I encourage you to come, all right? But if you feel like you've got a good handle on what is expected, you're welcome to use that time as you would. But I just want to do a brief overview of the assignment so that you guys can all get going on that. And what I'll do is I'll start a new, I'll do a separate recording on that. So I am going to stop the recording.